Morning, this is the day 15, or excuse me, unit 15, day 3 notes. So it's normal curve practice. And I posted a link to help with some of the homework questions from yesterday, but we're also going to do an example today that I think will help with some of those that people were asking about. So this very first one says the lengths of full-grown sockeye salmon are normally distributed, keywords there, with a mean of 29.2 inches and a standard deviation of 2.4 inches. All right. It says find z-scores for sockeye salmon whose lengths are 25 and 32 inches. All right. So as a reminder, z-score is your observed score minus the mean divided by the standard deviation. And of course, we could write that using notation, but it's perfectly fine to write it like that. All right. So for the 25, we can go minus the mean, which is the 29.2, divided by the standard deviation of 2.4. That should come out to be negative 1.75. And of course, you can quick double check on your calculator. Right. As for the 32 inches, do 32 minus 29.2 divided by 2.4. That's going to come out to be 1.17. So negative z-score means that you're below the mean. Positive z-score means you're above the mean. So those numbers should at least make some sense there. All right. When it says determine the proportion of the sockeye salmon population to the nearest percent that lies between these two, if it says determine the probability, determine the proportion, determine the percentage, any one of those, you're talking about calculating the percent between those two values under the normal curve. Right? So here's the negative 1.75. Here's the positive 1.17. We want all that stuff in between here. All right. So to be able to do this, like we did yesterday, it is a normal CDF. You have to tell it the lower bound, negative 1.75, because that's for the left. The upper bound, that would be the 1.17. And then the mean and the standard deviation, when you use z-scores, are always 0 and 1. Right? So to get to this, don't forget, it's second vars. So I'm going to show it on my calculator right here. Hopefully you can see it. So second vars, choice 2 is normal CDF. And then we're going to go negative 1.75. Whoops. Next one, we're going to positive 1.17. Keep the 0, keep the 1, and hit enter. So the probability that it falls between those two things is 0.8389, and it keeps going. So when it says to the nearest percent, we'd multiply this by 100, and this would be about 84%. So that's the chances that if you're, maybe catching fish, that it's between those two lengths, 25 inches and 32 inches. Right? So that's the first part. And now what we're going to look at is why do we bother to learn these z-scores, right? Why are they helpful? Right? So when we get to this next one, it says if the scores on a standardized test are normally distributed, we got a mean of 560, standard deviation of 75, answer the following questions using your z-scores. All right. Find the probability that a test picked at random would have a score larger than 720. All right. So calculate the z-score for 720. So subtract the mean, divide by the standard deviation, right? What that should come out to be is about 2.13. And now when it says find the probability that a test picked at random has a score larger than 720, I want to see a visual here. So get your best drawing skills on, because I want to see them on your homework and I want to see them on the test. So if here is, the mean at 560, 720 would be above it. And then we want anything above that. So that's a really good score here. All right. So that means that our normal CDF is going to go from 720 up to, brain fart, 2.13 standard deviations above the mean. So right here up to infinity is what I want to see. All right. And so in infinity, 1 times 10 to the 99th power, and then mean 0, standard deviation 1. Oops, there we go. Slide so you can see a little bit better. All right. So on your calculator, same thing again. Use that normal CDF, second, vars, and then we're going from 2.13 up to 1 times 10, raise it to the 99th power. Apologies, let me slide it where you can see it. And then 0, 1. All right, so it's a 0.0165 and so on. It says round to the nearest tenth of a percent. So don't forget, if that's 0.0165, you're multiplying that by 100. So we're looking at like 1.7% chance that you're going to get a score, or this person, if a person picked at random, not you, all right, would get a score greater than 720, all right? Which makes sense. There's not a lot of people that would score that high on an SAT, all right? Find the percentile of a test score at 500, all right? As a reminder, percentile, in terms of an SAT, that's all the people that you did better than. So yay. All right, so in this case, the mean's 560. They're saying a percentile for a test score of 500. So that's below the mean, but I still want to calculate who's everybody that's below that. So I'm adding up all the percentages below that. So in that case, that means my lower is going to be negative infinity. My upper here, let's calculate the z-score. So 500 minus 560 divided by 75. Mm-hmm. So you can grab your calculator. That comes out to be negative 0.8. So that when you do the normal CDF, now you've got your values that are going in. So the lower bound is negative 1 times 10 to the 99th power. Your upper bound is going to be negative 0.8. And then your mean is 0. Standard deviation is 1. All right, so those stay consistent anytime we use z-scores. So let me see if I can slide us all onto the screen here. So second, vars, and now just change it up. Negative 1 times 10. Use that little caret key, raised to the 99th. All right, negative 0.8. And then keep hitting enter. So here, it's 0.2118, which as a percent, move that over, would be about 21%. So about the 21st percentile, meaning that that score is higher than about 21% of all the students. And that means about 79% scored better than that. All right. Now I said I was going to talk to you about why the z-score is important. I thought that the ACT question was in here. Maybe my memory is failing me, which wouldn't totally shock me. Okay, so let me just talk really quick about why a z-score is important. So what a z-score does is it normalizes the score, meaning that instead of figuring out like is the grade 1 to 100 or like an SAT, is it 0 to 800 or whatever it might be, when you use z-scores, it brings it back to the basics. 0 is your mean, and then you go up and down from there. So it allows you to compare grades that don't have the same score. Perfect example of that is the SAT versus the ACT. Right now, you don't have to write that down. But if you're trying to figure out like which score is better, so like let's say you took your SATs and you got a, 1200 on it versus you took the ACT and you got a 27. I'm not going to fib. I don't exactly know how the ACT scored because I never took it. But you could compare. You could actually figure out what were the mean, standard deviation, and figure out which one is comparatively the better score. So that's where z-scores are used. You bring it back to that same basic scale that you can compare anything against. Right? With that being said, we're only going to do 2 last examples here with z-scores in them. So let me slide. Oh, there is part C. Oops. Okay. It says find the probability that a test picked at random would have a score between 500 and 600. All right. Well, we play the same game. You would calculate the z-score for this guy, calculate the z-score for this guy. Now, if you trust me, I'm going to shortcut a little bit and I will let you know what those z-scores are. The z-score for the 500 is negative 0.8 because we just did that one. The z-score for the 600 comes out to be about 0.53. All right. So when you're looking for the scores in between those, again, show the visual. So negative 0.8 and then positive 0.53. We want everybody in between here. So that means this is your lower bound. That's your upper bound. Your mean and your standard deviation stays 0 and 1. So we would do the normal CDF, and I can do that right here so that you can quick see it. And then we would go from negative 0.8 to positive 0.53. And you can see that the probability comes out to be about 0.49. So almost 50% of everybody should be in between those two scores. But since it says find the probability, I'm going to leave it as 0.49 because probabilities we want to keep as a value between 0 and 1. All right. Now, part D, I actually want to change the question to part D. So get rid of it. Pretend you didn't see it. All right. For part D, what I want to do instead is say, all right, well, let's say that 5,000 students took, this particular SAT. So my question is, how many of them should we expect to score between 500 and 600? All right. So this is like questions, I think it was 2 and 3 on the day 2 homework, right? As soon as you know the probability, now when it says, all right, how many then out of 5,000 or 10,000 or 200, whatever it might be, all you have to do in this case is you're really saying, what is 49%, right, of 5,000? That's what you're being asked. So take that 0.49, multiply it by the 5,000 people, and that will tell you. All right. Now we know it should be about half. So this should be pretty close to 2,500, but I could keep it exact on my calculator even. I still got it there. Times 5,000, and it's going to come out to be 2450.44, but these are people. So I would say about 2,450 students is what you would expect out of that group of 5,000. Now, is it a guarantee? No, all right? When we say things are normally distributed, it means that they follow that curve, but it's not an exact. If you have 2,453, whatever, it still follows the general idea, all right? So unless you had all the smartest kids ever take it, this is what you should be looking at, all right? And in that case, it would have a different mean and a different standard deviation for that particular data set, so. All right, now I said that's the last one we're going to use the z-score for. So next part says, what if we just skip the z-score part? Can we do that? Yeah, we can, all right? So if you're not comparing the data from 2 different tests where the scaling and the scores are different, there's actually not a big need to even use the z-score because you don't need to normalize it. So you get to skip that step. So when it says, for this one, given the volume of in a 12-ounce soda bottle from a factory varies normally, there's our key words, with a mean of 12.2 ounces. So you're actually getting a little more than 12 ounces. Woo. Standard deviation of 0.6. Use the calculator to determine the probability that a bottle chosen at random would have a volume greater than 13 ounces, less than 11, or between 11 and a half and 12 and a half. All right, so like the first case is saying like you get a little extra, greater than 13 ounces. I still want you to draw the picture. All right, so the mean is 12.2, which means 13 is up here. Greater than 13 means we're shading in that piece above it. Here's the cool part. The lower value is now just the 13. The upper value we're going to treat as infinity. And then we can plug it in from there. All right, now for some reason there's like a lot of space right here. So I'm going to slide up just a little bit. All right. And you're going to put those values right down here. So you're going to do the lower as 13, the upper as 1 times 10 to the 99th power. And now instead of the mean and standard deviation being 0 and 1, here's where you're going to actually have to use the real mean and the real standard deviation if you don't normalize it. So the mean is that 12.2 right there. The standard deviation, that's the 0.6. So it's super easy to use. But if you don't use z-scores, you have to make sure, right, to use the actual mean and standard deviation, right, for mu and sigma. All right. So just remind yourself, oops, I'm sorry, a little off the screen there. Okay, let's try it. So for this first one, remember second vars, normal CDF, and now 13 is the lower, upper we're going to treat as infinity, so 1 times 10 raised to the 99th, and then 12.2 and 0.6. And there you go. So the probability comes out to be 0.09. 1, 2, and now it says round to the nearest 10,000th. Ooh, so I need most of that. And now does it say percent or just probability? Okay, so we'll leave it just like this. So 0.091 would be the probability to the nearest, 10,000th. Oops, keep that too. 10,000th. We need that extra value. All right, but what does that even mean? All right, that means it's about, a 9% chance that the soda can that you get is going to have more than 13 ounces. So, all right, take your chances. I don't know. I don't even drink soda. Teach their own. All right, less than 11 ounces means you get the deal. Here's 12.2. There's 11. You'd be looking at that piece of it. So let's just talk about what the setup would be. In this case, make sure left to right. So the lower would be negative infinity. The upper would be the 11. So I'm going to slide here. Lower would be the negative 1 times 10 to the 99th. The upper is the 11. And then keep the mean at 12.2, the standard deviation at 0.6. And then same game for the last one. If I want values between 11.5 and 12.5, you just got to think about where that's going to be. So if the mean is 12.2, 11.5 is here. 12.5 would be up here. Now, it doesn't have to be scaled perfectly when you draw these, but if it's below the mean, it should be below the mean. And if it's above, it should be above. So I expect that level of accuracy, nothing much more than that. All right. So the lower is the 11.5, the upper is the 12.5, and then 12.2 and 0.6. Right. If you want to check your answers, this one comes out to be 0.0228. So it's about a 2% chance that they would really shortchange you on your soda and be less than 11 ounces. And then here, this one comes out to be 0.5697. So you're looking at about a 57% chance that the soda is going to be somewhere between 11.5 and 12.5 ounces, which makes sense. Those are values right near the middle. That's where the bulk should be. So more than 50%. All right. When you hit the next 2 pages, those are the homework. So when you send me the homework, I think tomorrow the homework is due. Just take pictures of the last 2 pages. It would be super helpful if you wouldn't mind writing, day 3 homework at the top if you print it out. If you're doing it on a separate sheet, I always expect you to label the top to give me a fighting chance to know what the heck you're sending me. All right. Otherwise, good luck with that. Let me know if you need help, and I'll see you at the Google Meet if you have any questions.